Hello everybody. Today we're going to be talking a little bit more about atmospheric pressure and the units in which pressure is measured. We try to stick with international units or SI units for this course, but pressure is one of those quantities where there are still a lot of situations outside the classroom where non-standard units are commonly used. It seems like the quantity of pressure is still expressed in more non-standard units than any other quantity. Since this can lead to some confusion, we will discuss some of these non-standard units of pressure as well. First, let's talk about the origin of atmospheric pressure. Where does atmospheric pressure actually come from? Remember, we said that pressure can be described as being the force divided by an area. Furthermore, the atmosphere weighs a lot. That means the atmosphere can provide a lot of force. This means that we're constantly subjected to really pretty high pressure, but we often don't even realize it. Let's talk about how the pressure or how the atmosphere affects pressure. First, consider this top-down view of the United States. Now, I want you to think about two specific locations in the U.S. First, here is Death Valley out in California. Death Valley is significant to our discussion here because it's the lowest point in the United States, at about 280 feet below sea level. Next, think about the Rocky Mountains. If we think about Pikes Peak, it is one of the higher spots in the Rockies, and it lies northwest of Death Valley. Now, to illustrate what these facts have to do with atmospheric pressure, imagine that we could rotate our view of the continent backwards, so that we were looking at the continent from the edge. This horizontal line represents the U.S. viewed edge on. Over here on the west coast is the Pacific Ocean, and over on the east coast is the Atlantic Ocean. Death Valley would appear as a whole right here. And this is Pikes Peak. This blue line represents the upper edge of the atmosphere. Above the upper atmosphere is outer space, where there's no air at all. Below that line is where there is atmosphere. Now, in reality, I know there's not a nice clean boundary like that where air ends and space begins, but for our purposes, it helps to think of it this way. Now, the weight of the atmosphere above us provides the force for atmospheric pressure. That means if we're standing on the beach in California, we would have a column of atmosphere piled on top of us that would be this tall. It would go from the ground all the way up to the very edge of the atmosphere, where outer space is. The weight of that column of air would provide the force that makes the pressure exist. Can you see that if we went to Death Valley and measured the pressure again, we would now have more air piled on top of us because we're down in this hole? The air pressure would measure higher. Similarly, if we go up on top of Pikes Peak, or any mountain for that matter, and measure the air pressure, the value would now be less because the column of air on top of us is now considerably shorter. Finally, if we go to a beach out on the east coast and take one more measurement, we would get a value very much like what we had back in California. Now, there are factors which cause the atmospheric pressure to vary a little bit from day to day, but in general, this is the important idea, that when the fluid pressure is being considered, the height of the column of fluid is very important. Mathematically, we write it like this. P, for pressure, is equal to the Greek letter rho. That little kind of cursive-looking P-looking letter is actually a Greek letter rho, and it means the weight density of the fluid. And so the weight density of the fluid multiplied by the height of the fluid column produces the pressure. Now, remember I said atmospheric pressure varies a little bit from day to day? That's because the weight density varies a little bit. Remember, density is affected by temperature. When air is hot, it becomes a little bit less dense, and therefore the pressure would be a little bit lower. If air was colder, it becomes more dense, and the value for rho would get bigger, and the pressure would get a little bit higher. But if we measure the average pressure from the atmosphere over a period of time, it will all average out, and it will be very consistent. So that then kind of raises the burning question, Well, how much exactly does the atmosphere weigh? Well, in answering that, it'll show how some of these other units of pressure came into being. So first, atmospheric pressure is measured with an instrument called a manometer, which is a really simple device. A manometer is just a U-shaped tube that's sealed off on one end. The tube is then typically tipped over, and it's filled with a liquid so that it can be filled all the way to the sealed end without trapping any air in the tube. Then, when you have the liquid in there, they stopper it up and rotate the tube back to a vertical position and take the stopper out. The liquid will kind of adjust, and you'll end up with this space on the sealed end that has absolutely nothing in it. It's just a pure vacuum. Now, let's consider what this would look like if we did it with just a U-shaped tube that was open on both ends. In this case, if the tube was open on both ends, everything is in balance. To show this, let me just put a line down the middle, and notice that we have the exact same amount of liquid on the left side of the tube as we do on the right, and therefore we would have the atmosphere pushing down on the left side of the tube and pushing down equally hard on the right side of the tube. Since you got the same amount of liquid on both sides, the weight of the liquid on the left would balance the weight of the liquid on the right. Everything is in balance. Now let's apply that same idea to our manometer over here on the right. First, let's put in that reference line, and notice that when we do that, everything is still in balance. Now it looks kind of weird because it doesn't look like it's balanced, but it actually is. Remember, in this space up here, there is a vacuum. That's not an air bubble. That is a space where there is nothing at all. Remember, they filled the manometer all the way up with liquid and then turned it so that as the liquid level came down, the liquid level dropped, but there is nothing trapped in that space up there. That is just a vacuum. Over on the right-hand side, you still have the atmosphere pushing down on the surface of the liquid just like we did in the open tube. But if we draw a line across here so we can compare the liquid levels, we can see that below that green line, the liquid in the tube balances. Below the green line, you have the exact same amount of liquid on the right side of the tube as you do in the left, which means that the liquid above that green line, from here to here, the weight of that liquid is what's actually balancing the atmosphere. So, as a result of using manometers, people began to just say, well, the atmospheric pressure is equal to the height of a particular column of fluid. And the fluid that was often used was mercury. In order to make the manometer as small and compact as possible, you want a liquid which is as heavy as possible. Well, mercury is an extremely dense metal which is liquid at room temperature. Now, it has some health hazards and it has some other issues, but in terms of being a liquid for a manometer, it turns out to be almost ideal. It works really, really well. And if you measure atmospheric pressure with a manometer like this over a long period of time, you see that the average height of the mercury column in the manometer turns out to be 760 millimeters. So the atmosphere weighs the same as the liquid in the extra column height, and since mercury makes a really, really good liquid to be used in manometers, that became just kind of the standard. And so atmospheric pressure, people typically just began to say, well, atmospheric pressure is 760 millimeters of mercury. Or if they were measuring in the Old English units, 760 millimeters is the same thing as 29.92 inches. So, because of how pressure was measured, we wound up with a whole lot of different units describing pressure. And a lot of those non-standard units are still around today. So let's talk about some of those other pressure units then. First, an atmosphere is one. An atmosphere is just the pressure of Earth's atmosphere. If we express this in terms of SI units, remember the standard international standard unit for pressure was newtons per square meter. Well, one atmosphere of pressure turns out to be equal to 101,325 newtons per square meter. So if on the ground at sea level you draw out a square 1 meter by 1 meter, And that column of air, which is standing on top of that, would end up weighing 101,325 newtons. But remember, a newton per square meter was kind of long and hard to say, so we shortened that and we just call that a Pascal. So standard atmospheric pressure, 1 atmosphere, is 101,325 pascals. Also, we tend to be lazy, and so remember we've talked about the prefixes that are used with units quite a bit. And here's we use kilo. 101,325 pascals is the same thing as 101.3 kilopascals. So that is the most common way you'll see standard pressure described. Standard atmospheric pressure is 101.3 kilopascals. If you look on the side of your tires in the United States, you'll probably have a specification on there that will tell you to inflate it to so many pounds per square inch or psi of air pressure. But there will probably also be a specification on there telling you to inflate it to so many kilopascals of pressure. We've already mentioned that another really common unit that we run into when dealing with atmospheric pressure is millimeters of mercury. So 1 atmosphere of pressure is exactly the same thing as 760 millimeters of mercury. If you're in the United States, you might hear a weather person talking about a high pressure or a low pressure system. They might say something like, barometric pressure this morning was 29.4 and falling. By that, they mean that the mercury column on the manometer was 29.4 inches tall. So 1 atmosphere is the same as a column of mercury that's 29.92 inches in height. Another unit you may occasionally run into is a bar. A bar is almost the same as an atmosphere, but not quite. 1 atmosphere of pressure equals 1.013 bars. Or you'll hear a prefix with it. The atmosphere is 1,013 millibars. Again, that's one that you don't hear as much anymore, but you will still run into that one. Finally, when measuring fairly low pressures of things, like measuring the pressure of gas in a gas line, or the amount of vacuum pressure produced by an engine when it's running, sometimes you hear those measured in terms of inches of water, because the manometer which is used to measure them has water in it. And so you might run into pressure in terms of inches of water, even meters or millimeters of water. And finally, one old one that still pops up occasionally is a torr. Sometimes you'll hear pressure measured in torr. Torr turns out to be the same thing as millimeters of mercury. So if something is given as a pressure of 500 torr, that's the same as 500 millimeters of mercury. So the main thing is that if you understand that pressure can not only be described in terms of force and area, but also in terms of the height of a fluid column and the density of that fluid, you'll be well on your way to understanding how pressure works in fluid systems. More later.